Swayam Prabha. Digital India. Educated India.
Welcome to lecture 22 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is shrinkage estimation and penalized regression. In last two lectures, we discussed the problem of multicollinearity. Then we also discussed different methods to overcome this problem. In fact, the problem of multicollinearity is the problem of sparsity. By sparsity, we mean we have taken observations on a large number of predictors, but only a small number of predictors, relatively small number of predictors have contributed significantly in the variation in y, but you are not able to select those predictors which have actually contributed significantly. We also observed that we cannot apply variable selection procedure, because our testing procedures test for testing the significance of a single regression coefficient does not work well. OLS estimator has large variance. So, ultimately we moved to the class of biased estimators. So, in fact, there is a trade off between bias and variance. If we try to decrease the bias, then it increases the variance. OLS estimator has bias 0, but it has very large variance. On the other hand, if we try to decrease the variance, it increases bias. So, then we look at the mean squared error. Now, in this lecture, we discuss some penalized regression estimators. We can use these penalized regression estimators to overcome the problem of multicollinearity also. In fact, one of the penalized regression estimator we have considered in the last lecture also, that is Risch regression estimator, and then we will discuss some other shrinkage estimators like Stein rule estimators also in this lecture. So, mainly we are going to consider two types of shrinkage estimators. The first is penalized regression estimators, and for defining the penalized regression estimators, your main objective is to overcome the multicollinearity problem or overcome the sparsity problem. And the second class of shrinkage estimators which we are going to consider in this lecture is Stein rule estimators. Your objective is to improve risk properties of the OLS estimator. In both the cases, we move away from the class of unbiased estimators and we consider the biased estimators. Now, suppose you have a large number of variables, and then suppose you are facing the problem of multicollinearity, and then you want to select a subset of variables which are important for explaining the variation in y, or which are important for your model. In variable selection procedure, actually variables are either retained or discarded. Then variable selection procedure often lead to high variance and prediction error. So, it does not work well. And then we also discussed another problem with the variable selection procedure. So, if we apply some test procedure like t test, then it does not work in the presence of multicollinearity. Now, we consider some shrinkage methods which are more continuous, means in variable selection procedure either we take the OLS estimator BI. So, suppose your estimator is BIV. So, it is either equal to BI or it is equal to 0. So, it is somewhat discontinuous kind of situation, but shrinkage methods provide more continuous and do not suffer as much from high variability. So, now we consider some shrinkage methods for estimating the regression parameters. Now, first we discuss the penalized regression estimators. Now, one of the problem of multicollinearity is that the estimator of regression coefficient vector, the OLS estimator BI, is large in magnitude. You have observed that expectation of B transpose B is much bigger than beta transpose beta. So, your estimators are very large in magnitude. So, that is why we think about considering shrinkage estimators. We shrink these estimators so that their length become smaller. So, in penalized regression estimators, we shrink the estimators by imposing a penalty on their size. Then we have two parts. One is the residual sum of square and the other is penalty given to the size of the estimator. So, we give penalty to size of the estimator. Now, we consider the problem of sparsity. By sparsity, we mean a large number of predictors recorded, but a relatively small number or proportion of strong effects. Means you have taken observations on a large number of predictors, but all the predictors are not affecting the variation in y. All the predictors are not properly explaining y. Only a relatively small number of proportion of predictors have a strong effect on y. Say, suppose you have gene expression data and you want to observe which of the genes or changes in which of the genes are going to affect say breast cancer. Then usually we take observations on a large number of genes. So, we take observations on a large number of predictors, but not all the genes are going to affect the breast cancer, or changes in not all the genes is going to affect the breast cancer or cause the breast cancer. So, your problem is to identify those genes which are actually causing the breast cancer. You have only a relatively small number of genes which are actually causing the breast cancer, and so you face the problem of sparsity. Then Bayes variance trade off. So, suppose we consider this general regression relationship y equal to f x plus u, and f hat x is the regression prediction. Then effectiveness of prediction is measured through squared error prediction, means y minus f hat x whole square. And then if we take expectation of y minus f at x square, then you get the MSE. And in fact, this is equal to expectation of y minus f x minus f at x minus f x. Then this is equal to bias of f at x whole square. Actually, you have two parts. The first part will give you y minus f x whole square, and this is equal to sigma square u. Then you have this part. Now, this is the mean squared error of f hat x. So, this is equal to variance of f hat x plus bias of f hat x square. So, you get this expression. Then estimators having lower bias have higher variance, just like the OLS estimator in case of multicollinearity. It has no bias, its bias is 0, but it has very high variance. And then estimators having lower variance have higher bias. So, if we move to the class of biased estimators and we increase bias, of course, it decreases the variance, but then you have to pay cost for it in terms of higher bias. So, there is a trade off between bias and variance, and then we tune the estimator and find the best possible trade off, and the best possible trade off you get when MSE is as small as possible. So, you try to reduce the MSE. Now, we consider Ridge regression estimator as a penalized regression estimator. So, Ridge estimator is obtained by minimizing the penalized residual sum of squares. So, you have residual sum of square y minus x beta transpose y minus x beta plus c times summation j equal to 1 to k beta j square, and we denote it by RSS C. So, the first part is the residual sum of square, the second part is the penalty term. So, if beta j or beta j square is large, then this term increases, or then this term gives more penalty to larger values of beta j's. So, this is the penalty term, and then you can write RSSC as y minus x beta transpose y minus x beta plus c beta transpose beta. And then we obtain Ridge regression estimator by minimizing RSSC. So, we minimize this with respect to beta. Actually, this is equivalent to minimizing y minus x beta transpose y minus x beta, subject to the restriction that summation j equal to 1 to k beta j square is less than or equal to some constant delta. Actually, these two optimization problems are equivalent. There is a one-to-one correspondence between these two. Now, we try to find out the expression for the Ridge regression estimator by minimizing RSS C. So, we minimize RSS C, and for that purpose we differentiate RSS C with respect to beta, and then we obtain del over del beta RSS C is equal to minus twice x transpose x beta plus this is plus sign, and then you have minus 2 times x transpose y, and then you get plus twice C beta, and then we replace beta by the Risch regression estimator. We write it equal to 0, solve it for beta, and then we write the final solution as beta hat Risch. So, the final solution is you get x transpose x plus c here, 2 will cancel out, you get x transpose x plus c, and then we take identity matrix inverse, and then you have x transpose y. So, this is the expression for Risch regression estimator. So, the solution adds a positive constant in the diagonal elements of x transpose x. We have C here. So, we have actually added C to each and every diagonal element of x transpose x, and C is the penalty parameter controlling the amount of shrinkage. Say if C is equal to 0, then you get the OLS estimator, there is no shrinkage, and if you keep on increasing the value of C, then the shrinkage factor increases. So, C controls the amount of shrinkage. Now, we consider the singular value decomposition of x. So, we write x equal to u d v transpose, where u is n cross k, v is k cross k, and these are orthogonal matrices. D is equal to diagonal d 1, d 2, d k, and we assume that d 1 is greater than or equal to d 2, so on greater than or equal to d k. These are the singular values of x. Then x is singular if any one of the dj's is 0. Then you can write x transpose x inverse x transpose equal to, we write x equal to u d v transpose, then x transpose x is v d u transpose u d v transpose whole inverse, then we have x transpose. So, v d u transpose. Then u transpose u is equal to identity matrix. So, you have v d square v transpose whole inverse. So, you get u d v transpose, then we have v d square v transpose whole inverse v d u transpose, and then this is equal to, we take inverse of this. Now, V is a k by k matrix. So, it is a non-singular matrix, a square matrix also. So, we take u d V transpose, then we have V transpose inverse, and since V is an orthogonal matrix, V transpose inverse is equal to V. Then you have d minus 2, then V transpose, then again we have V d u transpose. From here you obtain V transpose V equal to identity, V transpose V here also identity, then you have d d minus 2 d's, again you get identity matrix. So, this is equal to u transpose. Then or actually this is the predicted value based on the OLS estimator x b. Then this is equal to x transpose x inverse x transpose y equal to u transpose y. This is the OLS estimator, and then you have this predicted value. Then u transpose y is the coordinates of y with respect to the orthogonal basis u. Further, x beta hat ridge is equal to x transpose x plus c I k inverse x transpose y. Again this is equal to, we write x transpose x plus c I k equal to we get x transpose x equal to v d square v transpose plus c, you can write I k equal to v transpose. So, you get v d square plus c I v transpose. Then again we substitute the value of x here, which is equal to u d v transpose. So, you get u d v transpose, then you have v again here, then d square plus c I inverse, then you have v transpose, actually you get v here, then u transpose y. Again v transpose v is identity, and then actually you get v transpose here also. So, this is also identity, and then you have d u transpose y. So, you get this expression, and then you can write it as summation j equal to 1 to k u j d j square upon d j square plus c, then u j transpose y, where u j is the jth column of u. So, actually the ridge regression shrinks the coordinates of y with respect to the orthogonal basis u by the factor d j square upon d j square plus c. If you look at the expression for this ridge regression estimator, then this is the shrinkage factor. So, it shrinks the coordinates of y with respect to the orthonormal basis u by this much of factor. Then greater shrinkage is applied to coordinates corresponding to smaller values of d j square, and then d j square is equal to lambda j, the jth eigenvalue of x transpose x. Now, in defining ridge regression estimator, actually we have minimized the residual sum of squares, and then we have also incorporated a penalty term in the residual sum of squares, which is c times beta transpose beta, or c times summation beta j square. So, actually you have a L2 penalty in ridge regression estimator. This was your L2 penalty. Now, in lasso or least absolute shrinkage and selection operator, apart from this error sum of squares, we have a L1 penalty here. So, we take c times summation j equal to 1 k mod beta j. And then we obtain the lasso estimator by minimizing this quantity. So, beta hat lasso is argument minimum over beta y minus x beta transpose y minus x beta plus c times you have L 1 penalty summation j equal to 1 to k mod beta j. Or equivalently, you can write lasso as beta head lasso equal to argument minimum beta y minus x beta transpose y minus x beta subject to the restriction that summation j equal to 1 to k mod beta j is less than or equal to delta. So, these two optimization problems are actually equivalent. Now, actually lasso solution is a quadratic programming problem. Again, I am not going into much details how to get the lasso estimator for a given C. It is a quadratic programming problem. Now, if delta is larger than say delta naught equal to summation j equal to 1 to k mod beta j, then beta head lasso is equivalent to B. So, then there is no shrinkage. And if delta is equal to delta naught by 2, then you can say the amount of shrinkage is 50%. So, actually you are taking summation j equal to 1 to k mod beta j less than or equal to delta, and delta naught is equal to summation j equal to 1 to k mod beta j. So, if delta is equal to delta naught by 2, then of course, it shrinks all the estimators and the shrinkage is 50%. Now, what is the difference between regression and lasso apart from this penalty factor? In regression we are taking L 2 penalty and in lasso we are taking L 1 penalty. Then what is the other difference? Actually, if you plot the Ridge regression against C like Ridge trace plot, then the estimator never becomes 0. But if you consider lasso, if you plot different estimators against C, then as C increases, your estimators move like this, or it may move like this, or for negative values it may move like this. So, you see that for any particular C, some of the estimators are becoming 0. So, if you select C here, then this estimator is 0, this is 0, this is 0, but here you get a non-zero estimator. So, actually this lasso solution makes some of the estimators equal to 0. So, it is actually serving dual purpose. It is selecting the relevant variables, making some of the regression coefficients equal to 0 means the procedure is not selecting those variables, and then it is shrinking the other estimators. To make the things more clear, let us consider the case of two variables. Say residual region has elliptical contour, this is the residual region. In Ridge regression you have the restriction beta 1 square plus beta 2 square less than or equal to delta. So, it is just like this circle. In Lasso, the term penalty term is, or the restriction is mod beta 1 plus mod beta 2 less than or equal to delta. So, it is somewhat like diamond. Then in both the methods, we find point where elliptical region hits constrained region. So, we try to find out this point or this point. Now, in which case your constraint region is a circle, then it cannot hit, this ellipse cannot hit the circle region at 0. But here in diamond constraint or in lasso constraint, you find these corners, and then this elliptical region can hit this corner. So, your estimator become 0, estimator of one of the parameters becomes 0. So, ridge regression estimator does not serve the purpose of variable selection, but lasso does both the things. It selects the important variables and it also shrinks the regression parameters of other, or estimators of regression parameters of other variables. Then sometimes one can use LQ penalty. So, in LQ norm penalty, we have the penalty factor C times summation j equal to 1 to k mod beta j to the power q. Obviously, for q equal to 1, you get the lasso penalty, and for q equal to 2, you get the ridge penalty. Or one can go for elastic net penalty. This is actually a compromise between ridge and lasso. So, the penalty term is like this. So, C times alpha into summation j equal to 1 to k mod beta j square plus 1 minus alpha into summation j mod beta j. So, here you have ridge penalty and lasso penalty. Of course, alpha lies between 0 and 1. Again, for alpha equal to 0, you get lasso penalty, and for alpha equal to 1, you get ridge penalty. And for any value of alpha between 0 and 1, it is a compromise between ridge and lasso penalties. Then another problem is the choice of regularization parameters C. How to choose C? In ridge regression, we have discussed some of the procedures for selecting the value of C, like ridge trace or some operational values of C. But in all other methods, like if you take lasso penalty or LQ norm penalty or the elastic net penalty, then you do not get such kind of simple values of C. One can go for k-fold cross validation to obtain the value of C. In k-fold cross validation, what we do? We divide the data randomly into k groups, and then we construct the model based on k minus 1 groups. So, k minus 1 groups are used, all the observations in k minus 1 groups are used for fitting the model, and then we validate the model on the kth group. So, for instance, on the basis of observations of these k minus 1 groups, we fit a multiple linear regression model and then we predict the values of y for this kth group. Then you must have some kind of prediction error. You know the actual values of y, you know the predicted values of y based on these k minus 1 groups, observations on these k minus 1 groups. And then you can repeat this process. You include this group here and then you take one more group from here and then you validate the model on that group. So, you repeat this process, you keep on changing the groups, but each time you take k minus 1 groups for constructing or for fitting the model and then you select the remaining group for validation purpose. Now, sum of squares of prediction errors for each model is an estimate of squared prediction error. So, for selecting the value of C, what we do? We do this kind of cross validation for different values of C. Then we select that value of C for which estimate of squared prediction error is minimum. So, this is how you can get an operational value of C. You can apply this method for ridge also for obtaining the value of C or for the lasso or for elastic net, etc. Now, we come to a class of shrinkage estimators which is known as James-Stein estimator. Again, suppose y is k cross 1 vector on a single observation from normal distribution having mean theta and variance sigma square I k. Then MLE or least square estimator of theta is y. You have just one observation from this multivariate normal distribution. So, obviously, the MLE is the same observation MLE of theta. Then Stein in one of his work in 1956 and then again James and Stein in 1961 showed that for k greater than or equal to 3, y is inadmissible, and if you take the mean squared error, that is theta head minus theta transpose theta head minus theta, then this biased estimator theta head equal to 1 minus k minus 2 sigma square upon y transpose y into y has lower risk than y or lower risk than the MLE. So, obviously, this y is an unbiased estimator of theta, whereas this theta head is a biased estimator, but still this estimator has lower mean squared error than this unbiased estimator. So, this provides an improvement over y. So, this result was given for multivariate normal distribution. So, using this approach, we can develop an improved or an improved biased estimator for estimating the regression coefficient vector of a multiple linear regression model also. So, now we consider Stein rule estimator for linear model. We consider the model y equal to x beta plus u follows a normal distribution having mean 0 variance covariance matrix sigma square u eigen. Y is of order n cross 1, x n cross k, beta k cross 1 and u is n cross 1. Then this is your OLS estimator of beta, and the distribution of OLS estimator is normal with mean vector beta and variance covariance matrix sigma square u x transpose x inverse. Further, suppose you write W equal to y minus x b transpose y minus x b. then W upon sigma square u follows a chi-square distribution with n minus k degrees of freedoms independently of B. So, we have the distribution of B, we have the distribution of W upon sigma square u. Then just like the Stein rule estimator for multivariate for the mean vector of multivariate normal distribution, the Stein rule estimator here of beta is defined as beta hat s equal to 1 minus say A w upon B transpose x B into B. So, this is the class of Stein rule estimators. Now, for proving the dominance of beta hat S over V, we require the following results. Actually, we have already proved these results in lecture 3, when we were discussing the multivariate normal distribution. Say Stein's univariate lemma, if Z follows normal 0 1, G is a function from R to R and G is absolutely continuous with derivative G dash Z, and then we assume that expectation of mod G dash Z is finite, then expectation of Z G Z is equal to expectation of G dash Z. So, for proof of this result you can go to lecture 3, and again if Z is k by 1 vector, then Stein's multivariate lemma states that if Z follows normal 0 I k and G is a function from R k to R, which is absolutely continuous and differentiable with this derivative del G Z, then expectation Z G Z is equal to expectation del G Z. And then you can generalize this result for the case when y follows normal theta sigma square I k. In this case, we have expectation of y minus theta g y is equal to sigma square expectation del g y. So, the proof of all these results are given in lecture 3. Now, we consider the quadratic loss function. L beta hat beta is equal to 1 upon sigma square u beta hat minus beta transpose q beta hat minus beta, where q is a k by k positive definite symmetric matrix. Then the risk function is R beta hat beta equal to 1 upon sigma square u. We take expectation of this loss function. Actually, this function is expectation of L beta hat beta. So, we have 1 upon sigma square u expectation of beta hat minus beta transpose q beta hat minus beta. Now, suppose lambda max C is the maximum eigenvalue of the matrix C, means maximum eigenvalue of the matrix inside the bracket. Similarly, lambda min C denote the minimum eigenvalue of C. Then, for any k by 1 vector x, x transpose C x upon x transpose x is always less than or equal to lambda max C and greater than or equal to lambda min C. This result you can easily verify. And in fact, if you take an orthogonal matrix P such that P transpose C P gives you, this is a diagonal matrix with diagonal elements as the eigenvalues of C. Here you have eigenvalues of C. Then you can write x transpose C x as x transpose P P transpose C P x, and then you write x transpose P equal to say V. So, you have V transpose, and then in between you have the matrix of eigenvalues of C, and then you can easily verify this result. So, now we have this result 22.1 under the loss function 6, the Stein rule estimator beta hat S has lower risk than the OLS estimator B. Whenever A lies between 0 and 2 upon n minus k plus 2 d minus 2, where d is equal to trace of lambda inverse q upon lambda maximum lambda inverse q, and we assume that d is greater than 2. Otherwise, this condition will not be satisfied, and then we are writing lambda equal to x transpose x. Now, the risk of beta hat S can be written as R beta hat S beta equal to 1 upon sigma square u. Then you have expectation of beta hat S minus beta transpose q beta hat S minus beta, and then we substitute the value of beta hat S here. So, we obtain B minus beta minus A w upon B transpose x b B here, and then we have transpose of this q, and then again we have the same vector, and then we multiply it. So, we get 1 upon sigma square u expectation of B minus beta transpose q B minus beta. Now, this is the risk function of OLS estimator. Then the second term is minus twice A expectation of B minus beta transpose q B w upon B transpose lambda B, and then you have the square term A square expectation w square upon B transpose lambda B square, then you get B transpose q B. You get this term when you multiply this by this, and in between you have q. Now, you take the difference between the risk of B and beta hat S, which is now equal to this term will cancel out, and then here you get plus sign and then minus sign. So, you get 1 upon sigma square u twice A expectation B minus beta transpose q B, and then you have w upon B transpose lambda B minus A square expectation of this term. And then we write z equal to 1 upon sigma u lambda minus half b, and theta equal to 1 upon sigma u lambda minus half beta, and v is equal to w upon sigma square u, and then we write q star equal to lambda to the power half q lambda to the power half. Then z and v are independently distributed. Z follows normal theta I k and v follows a chi square distribution. Further, the difference between the two risk delta becomes in terms of z and v twice A expectation z minus theta transpose q star z, and then we have v upon z transpose z here minus A square expectation of v square upon z transpose z square z transpose q star z. And since v follows chi square distribution independently of z, so expectation of v is equal to n minus k, and expectation of v is square is equal to n minus k plus 2. And then here we use the Stein's lemma. So, we can write expectation z minus theta transpose q star z into 1 upon z transpose z in this form, del over del z q star z 1 upon z transpose z, and then we have this second term here, and then we differentiate this term with respect to z, and we obtain, actually when we differentiate with respect to z, this term we get trace of q star, and then if we differentiate 1 upon z transpose z, then we obtain 1 upon z transpose z square twice z transpose. So, finally, we obtain this expression. We can take A n minus k outside, and inside expectation we have twice trace of q star 1 upon z transpose z minus 4 z transpose q star z upon z transpose z square minus A n minus k plus 2 z transpose q star z upon z transpose z square. And then this is greater than or equal to A into n minus k, we have this term. So, here actually we have used the inequality that z transpose q star z upon z transpose z is less than or equal to the maximum eigenvalue of the matrix Q star, which is equal to the maximum eigenvalue of x transpose x inverse Q. So, we get this result, and then for delta greater than or equal to 0, we have twice d minus 4 minus a n minus k plus 2 greater than or equal to 0, and then this leads to the condition 8. In terms of A, you can find the condition 8. So, we get the dominance condition for the James-Stein estimator. Now, B is the minimax estimator of beta. So, 8 condition is for beta hat has to be minimax. Then in particular, if you take Q equal to x transpose x, you get this condition, dominance condition, and when we take Q equal to I k, then we get this dominance condition. So, these are two special cases. We also observe that the width of the interval determines the amount of shrinkage allowed for minimixity, and it is positively related to k, negatively related to n. K increases, the width increases, n increases, the width decreases. Then the condition number, this lambda minimum capital lambda trace lambda inverse minus 2 is greater than 0, fail to satisfy if multi collinearity is severe and lambda minimum is very small. So, in this lecture we have discussed different penalized regression estimators and shrinkage estimators. In particular, we have discussed Lasso, the least absolute shrinkage and selection operator, and ridge regression estimator. Lasso uses L1 penalty, whereas ridge regression uses L2 penalty. These estimators are used to overcome the problem of sparsity, that is, when you have a large number of predictors under consideration, but only a small number of predictors are actually contributing to the variation in y. Then we have also discussed another shrinkage estimator, which is James-Stein estimator, and then we have derived the dominance conditions for the James-Stein estimator over the least square estimator under quadratic loss function. So, I am going to stop here. Thank you.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally, even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used and it became popular during World War II in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Dantzig is considered the father who really proposed the technique of linear programming as a very nice tool where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that things have really moved very fast, they have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system and so on and so forth. In the coming years, it is thought and definitely with some positive viewpoint that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example you want to basically have a layout such that minimization of cost is one factor and the maximization of say for example benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add-on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.